And now you can, okay, again, we have this, let's say there's an initially uncharged capacity, just two plates separated by 2 millimeters. And you hook up a 1.5 volt battery. What's going to happen is positive charge is going to be repelled from here and end up here. Negative charge will be repelled from here and end up here. Now, in reality, if this is metallic conduction, it's just negative charges that get to move. So what happens is your negative charges on this plate get attracted to the positive. Okay. And get pushed by this negative terminal onto the negative. Now, there's some details in that process, but that's the way it's going to work out. So you're going to end up with positive charges here. Negative charges here. Now, my question was, you know, what's the electric field, and do I have the arrows in the right direction? If we see and think of this as positive charges being pushed here, negative charges being pushed here, or some combination thereof. In this case, only negative charges being pushed here, but where they coming from, they have to be pulled from here. Their source doesn't have any stored up charge. This is a battery. Okay. Battery just has chemicals and anode, cathode, react in such ways to move charge. So this is the way. Okay, so we ask for the electric field, and of course we know the voltage. Because after you hook this up, this whole process transfers very quickly. And pretty soon there's no current. There's no current, there's no voltage drop across the wires. Of course, in the ideal situation, your wires have zero resistance, so instantly you end up with a voltage here that's in the opposite direction of the voltage. Okay. And we actually talk about this. I'll just throw out the terminology for now. You have a voltage drop of 1.5 volts from here to here. And you go up here and you have a voltage rise or negative voltage drop of 1.5 volts. Okay, so you go process, voltage drop by 1.5 volts. You go process it rise by 1.5 volts. The total voltage around the circuit is zero, as it has to be because the forces are conservative. And voltage is difference in potential energy per unit of charge. So if you go from any point on the circuit around to that same point on the circuit, voltage change has to be zero. Okay. We'll put all that together. Now that gets into circuit electricity, which is the chapter after the one we're doing this with. Okay. So the reason this out, the electric field is the number of newtons per coulomb that you would experience at test charge in here. And your potential difference is number of joules per coulomb. In 2 force. Okay. Well, number of joules would be the force times the distance over the number of coulombs. So we get the formula involving my friend Ed. Right? The force per coulomb is E. And the distance is D. This tells you if you have 1 coulomb here, it experiences a force of QE. That's just charge times it. And the work is then the test charge times E multiplied. Sorry, the test charge. Yeah. Okay, well, the force times distance, okay? If it works out, you need to think that through. You can think it through in terms of the meaning of the units, as opposed to memorizing the formula. You should do both. Because if you understand what's going on here in terms of forces and distances and changes in potential energy, then you're unlikely to pull the wrong formula in a given situation. Okay. Okay, well, anyhow, that's what we have. Okay, so you can work that out. So be 1.5 volts over 0.002 meters. Which is 1.5 joules per coulomb over 0.002 meters. And that's going to be 7,500 joules per coulomb. Work out and think about the units and how they are embodied in this situation. If you totally understand that, then you don't need big formulas to analyze what's going on with the capacitor. There are formulas, but there's a different formula for spherical capacitor than there is for cylindrical capacitor than there is for parallel plate capacitor. You want the concept rather than three different formulas. Okay. Okay. So by reasoning, that ought to come out right. Now my question is, how much charge is there on these plates? Well, I haven't given you enough information to find out how much charge. Okay. Now I have. What can you determine? If you know the electric field of capacitor. Well, you can go back. Gaussian surface. We can say, okay, well, if I do Gaussian surface here and the closing charge sigma times cross-section area of the cylinder, and half the flux is coming out this end, half the flux is coming out that end. Okay, so the field must be 2 pi k. And that's a bit of reasoning you really want to be able to understand that. Then you do a Gaussian surface over here and find out that the accurate is 2 pi k as well. The 2 pi k you get off of here, and the 2 pi k you get from here are in the same direction, away from the positive toward the negative. We can reason it out as opposed, E equals 4 pi k sigma. And we established that in chapter in Gauss's law, which some people had some trouble with. Okay. So you want to take some of the questions I gave you, see if you can do those. ask me or email me, whatever, but. I think simple Gaussian surface for. I say for an infinite plate, these aren't infinite plates, but for points closer to the plates than to the edges. That's going to be electric field. Okay, well, how much charge is on the plates? I'll use Q for the charge of the plates. And it's just the number, the amount of charge per unit area times the area of the plates. So it's real easy. Okay. We do it in 2 steps. Of course, you can solve this for sigma, it's E over 4 pi K times A. Of course, E is your voltage over your plate separation D. It could be written this way. Assuming I've done all that correctly, and I think I have. I'm going to check it. Do it yourself. Work it out without looking at what I did. Okay, so now the capacitance of a capacitor, because this is a capacitor, is the charge to area ratio. Okay. Capacitance all right, from the fancy C to distinguish it from the capital C we use for coulombs. A big capacitor is one that stores a lot of voltage or a lot of charge for a given voltage. Okay, what we do with this capacitor, if we want to store a lot of charge, the charge density is determined by the electric field. The electric field is determined by the voltage and the separation of the plates. It doesn't care what the area is. The electric field is what it's going to be, and the separation of the plates is what it's going to be. So if we want to store a lot of charge, we'll use a big area. Instead of these 10-centimeter plates, a couple of plates the size of football fields. Okay. And put them closer than 2 millimeters. Because the closer these are, less voltage you're going to have across them for given charge density. And the more charge you're going to be able to put in these for given voltage. Well, you got to sort through all that. If you want to understand it at that level. Okay. So capacitance is charge per unit, charge per volt. Okay, big capacitor, lots of charge for every volt. Take this 1.5 volts here and make the capacitor much bigger. We get a lot of charge for that 1.5 volts. If we want to put 150 volts on it, we get even more charge. Okay. Well, if the capacitance is Q over V, then what's your capacitance in terms of A and D? I don't know. Take what you have on the board. See how it works together. Okay, capacitance is Q over V, but we have Q in terms of sigma and A, but here it is in terms of A and D and V, right? I'll use a 4 pi K. Epsilon naught AB over D. Divided by V. And there's no need to write V as E times D. Because these were our variables, do it in terms of A and D. And if we just divide these D's out, you know. I said I was going to do it in terms of K, then I did it in terms of epsilon naught. Okay. And that is how I wanted to look it up in the book to make sure that you're using epsilon naught. Okay. Right. Okay, is Mr. Constant, okay, 9 times 10 to the 9th, meter squared per coulomb squared, just a tiny bit less than 9. Epsilon naught's a permittivity. Okay, and that's permittivity of free space. Air doesn't exactly have permittivity equal to that of free space. Okay, it's got a little bit of, there's a little bit of ionization that takes place, but it's really small. Okay. So air is pretty much the same as free space, except that you get ionization if your electric field gets big enough, 20 meters, which gives a path current. Once the air is ionized, the positive charges can run over here and the negative charges can run over here. And if you got ions, that happens if it goes both ways, but it neutralizes charge and defeats the purpose of the capacitor, unless your purpose is to make big sparks. Okay. Okay. So nothing mysterious about this if you understand how we get from here to here. Okay. Well, capacitor get used to a lot of things. We'll talk more about it when we play with them in the lab. If we want to think about what happens now if we have two capacitors. So now we've got two capacitors. We'll say this capacitor has capacitance C1 and this one has capacitance C2. And we're not going to worry too much about that formula, although you want to be able to derive that formula in terms of meters anytime you need it for a parallel plate capacitor. You can always memorize it, but that doesn't mean you understand it. And if you use it to get the right answer, as engineers, that is kind of the bottom line. But the more you understand, the better you're going to be if you happen to be designing circuits, the better you're going to, better feel you're going to have in the system. I think depends on how your brain is wired. For here, it's more economical to be able to understand everything and put it together than it is to memorize a bunch of stuff. Because here, we're really talking about how you solve problems, how you remove problems. Two formulas you gotta remember. More economical. Okay, well, so we got these capacitors. Now we got a voltage here. Let's use this symbol for the EMF. It'll be specific. Voltage your source. And maybe we could have resistance in here, but let's assume it's resistance. Okay, so the question is, what's the voltage across here and what's the voltage across here? Everything on the right, so we'll set else on the right. So we'll call this C1, we'll call this C2. My voltage here, if I tap off a little bit of current, put it through a meter. Okay. Get my voltage. And I've got a voltage across here. Out of those voltages add up. And well, what you have is total charge on these two capacitors. Now, on these two plates that are connected by conducting wire. These things have to have equal charges, equal and opposite charges. Okay. So if we look at these two capacitors, here we have Q2 on this plate. Well, actually, I'm just going to say we have a charge Q on this plate. We have a charge Q on this plate. Charge negative. So what's the charge here and what's the charge here? Well, the charge here has to be negative Q and the charge here is Q. Okay. These charges have to be equal and opposite. And whatever electrons this pulls off of here, end up here. Okay. Then when you got a bunch of electrons here, this is negatively charged. This is a color here. This system is a continuous conductor. Okay. The negative charge here is going to pull positive charges from this conductor. It's going to induce a positive charge here. This positive charge is going to push positive charges off of this or pull negative charges toward it. One way or another, this is going to end up negative, this is going to end up positive. The voltage across here voltage is going to be Q over C1 and Q over C2. Some of your voltage is the voltage of the source. Q over C1 plus Q over C2 equals the voltage of the source. And C total is the equivalent capacitance the two capacitor series then Q over C1 plus Q over C2 equals Q over C. Because if you look at the two capacitor series, how much charge has been transferred from one side of this combination to the other? Q. Okay. A charge negative Q has been pulled off of this plate and put onto this plate. And you don't care about what's in between. But whatever's in between, these charges have to be equal and opposite. Okay. So that's how we get this. You want to think about that. You want to think the charge is being pulled off of here, pushed onto here. Charges are pushed onto here, induce an opposite charge here. Charge has been pulled off of here, there's some charge behind which induces an opposite charge here. Giving you this. So if you divide Q out, you have this. And if you have worked some with circuits, you know that this is very much analogous to the formula for the equivalent resistance of a parallel set of resistors. Okay. Now, by contrast, if we have two capacitors in parallel, what that means is capacitor C1 here, capacitor C2 here, and a branch of the circuit that allows whatever current flows in the, let's say in the transient, when we just hook this up, okay, just for a short time, current flows, positive charge here and here, okay? Charges of both capacitors. Got the voltage of the source. Now, the charges on the capacitors don't have to be equal. They do have to be equal. Let's make sure we understand they do have to be equal because you have zero net charge between this plate of this capacitor and this plate of this capacitor. So we have the voltage of the source and pushing positive charge, actually pushing negative charge onto this plate and onto this plate. Pulling it off of this plate and this plate independently. the net change in potential around just this loop has to be zero. So, all my good colors are over here. Okay, so drop a zero around the C1 loop. Implies that voltage process capacitor is equal and opposite of the voltage of the source. Okay. Now, when I did this over here, I didn't concern myself too much with positive and negative, because we're just looking at the magnitudes of V1 and V2. Okay. But here I'm going to write it out. Picture of a standard contaction. Okay, so anyhow, we got C2 here. Voltage of the source here. So if we travel around this loop, we travel from any point on this loop and back to it. Whether this loop is here or not, we travel any path around this loop. When we get back to our starting point, we're going to have experienced zero change in potential. Conservation of energy, stored forces. V2 equals negative V source. Well, V1 is what? X Q1 over C1, right? V2 is Q2 over C2. They're equal. So what's the total charge? Then pull over here. Total charge has been transferred. Well, you look at this as a whole. total charge is Q1 plus Q2, your voltage is magnitude of the source. At this point, we're not interested in the negative, but I'll write it down over here. Okay. What's Q1 equal to, what's Q2 equal to, and what's the total capacitance equal to? In terms of C1 and C2. B source. Tell me what you got. Okay. Well, Q1 is source voltage over C1, right? We'll use a negative. This and this follow immediately from what I've written here. Your total capacitance is, and it's actually magnitude of charge over voltage. It's going to be Q1 plus Q2 is going to be negative C1 minus C2 times V source, right? The source factors out. And we got the absolute value signs, so we don't worry about the negative signs. We got C1 plus C2 times V source divided by the voltage, which is just V source, right? The same voltage across both. You got C1 plus C2. Now, the essence of this one is you have the same voltage across both capacitors. Okay, so this simple premise that you get from just basic principles. We have everything we need to rederive these formulas if we need. Or to make sure that they're right. Getting the test under the pressure of the day, not having slept for a week. Well, it must be hard to remember these premises, but probably easier to try to memorize which formula works. Okay, you know why the formula works, then you have some mastery of the formula. Okay. Now, we want to talk about the energy and capacity. Now, you've done problems. How much energy does it take to assemble this charge configuration, right? Some of the problems can be a little tricky, and somebody has some problems with those. Unfortunately, we don't have time to really address right now and try to figure out how to do that. Yeah, I took a pretty good look at work last night. Again. This way of this stuff, at least. And. Preferably at least 3 sessions. Instead of trying to pull it all together in one marathon on Sunday. Okay. Now, life might not let you do that, but try to spend at least a reasonable amount of time. It's only half hour. You know, looking over the problems, thinking about getting your brain working on them rather than trying to do it all at once. And make sure, of course, you spend a substantial number of hours each week on this. Okay, well. Energy. Let's say we got this. Earlier today. Now, this is a resistance, and you don't really have to have a resistance. If I put a resistance in there, it slows down the current so that the charging doesn't happen like it's, or it doesn't feel like it's happening. Nothing I'm going to do here requires a resistor. Okay. All we want to know is this thing is initially in charge. Okay, so here's our capacitance. Okay. No charge. Well, let's actually say that, yeah, we got some charge. Got a charge Q, and we add a charge delta Q. How much energy does it take to add delta Q? Okay. If we've got charge Q and the capacitance is C, the voltage is V source, but we don't need to know V source to answer these questions. We can ignore V. There's some voltage, and the capacitor is at less than that voltage, so we can transfer charge. Okay. How much energy does it take to transfer that charge? What you can think of is pulling some delta Q off of here and putting it over here. So we're essentially transferring a charge from here to here. That's the charge delta Q. How much energy is required? What I see is some people looking at point charges, pulling out the reciprocal R that would apply to point charges. And you can actually do that if you want to integrate over all of these surfaces. Okay, but you really don't want to do that. That would be really complicated. Okay, and some people try to work it out in terms of the electric field, you multiply the electric field by this charge in the distance, and you get it. You could come at it from that point of view. So I see some of that. I see some equations, you know. One thing that we really want to think about is that we have a definition of capacity. Might be a good place to start. Because, well, what can we determine from this? What do we know? What are we given? So what can we figure out? Okay, the whole idea of reading in terms of the units and stuff like that, we pull that together right. It'll eventually lead you there. But they're going to be like 3 or 4 steps in the reasoning. And you can kind of cut through it if you use this. Well, if C equals Q over V, are you given any of these quantities? Well, if the capacitance is C and you got charge Q. V equals Q over C. So we know the voltage. And we're asked how much work it takes to transfer charge to the Q. Okay. Work is work per unit charge times charge. You might think of it that way. Or if you make working with units, you say, well, it's joules over joules. Joules over coulombs times coulombs, right? Which isn't a bad thing to say. Okay, now how much charge are we talking about? We're talking about Q or delta Q. But we're not transferring charge Q, it's already there. Transferring charge delta Q. And the work per unit charge is a voltage. Okay. That's Q over C times delta Q. Transfer Q max equals C times V source. Work is the sum of all your Q over C's. Times delta Q's. Which is the interval from 0 Q max. Up Q over C times VQ. Now, well, you all work that interval out, which would take in a couple of seconds. I'll do something for that. Rewrite that a little bigger. Okay, so first of all, the integral is really easy. You know, integral Q over C dq. Assume you've written it out right. Take a look in a minute, okay? Process. You know, if you start with the uncharged capacitor, you got charge 0 on the capacitor. Okay? And when you transferred charge Q max C times V source. Okay, well, C times V source is going to give you voltage. When voltage across here. So I give you the charge when the voltage across here is equal and opposite to this. Okay, voltage here is going to be V source in the opposite direction, but it's still negative to this V source. It turns out it doesn't matter if it's positive or negative, it's going to end up being squared through the integral you see one. And you can think in terms of the incremental charges and how well it's charging negative, then the work done is kind of equal and opposite, stuff like that. So it all works out. So you just do this with a typical increment. That's how you think about it, setting up an interval. What happens over a small interval of what? Well, what is how much charge is on this thing? Charge is going from 0 to Q max. That's what happens in a typical interval. And then we can write it out like this. We partition the Q interval from 0 to Q max equals C times V source. Typical interval for delta Q, typical increment is a delta Q with existing charge Q star. Requires this much work, which is just conductor. Except I wrote in terms of Q star. So the total is the sum of all that, and that approaches this interval. And that equals Q max squared over 2C. Integrated with respect to Q. What's the antiderivative? C is constant with respect to Q. It's constant in this situation. If you're integrating Q with respect to Q, you're going to get Q squared over 2. So there it is. And of course, that could be written. This is the way you want to remember it. Okay, but of course, Q max is C times V source. So that's CV source squared root of 2C, which equals CV squared over 2, if I did that right. I always want to be thinking, okay, well, I've got Q max, we've got a formula for Q max squared, so we might as well see what we get if we put that formula in here in the square root of the okay. And you got to get a C squared here, it's divided by this C. The V source squared, that 2 is still going to be there. Check out the units, make sure it works. There's the energy unstored, uncharged capacitor. Okay, here's perfectly good capacitor. Okay, we can figure out what its capacitance is. We've already got all the stuff we need. A 10 centimeter radius. And we know what the area of each plate is. We know the separation. We can figure out what the capacitance is. Really tiny. Okay, really tiny. Now, if we put a piece of foam in here, that foam doesn't conduct electricity very well. So we can probably hold a pretty good charge on here. So the foam actually kind of helps with the gapping of electricity, although that happens in other parts of this apparatus. So it's still a problem. But theoretically, that could be helpful in preventing the air from breaking down. If the foam doesn't ionize and break down, and the foam is going to do that. The other thing that happens with foam, if this plate is positively charged, it's going to pull negative charge from this side of the foam. Okay. And if this is negatively charged, it will pull positive charge. And the details of that, how you insulate and everything, are important. We're not talking about designing capacitors. We're talking about understanding the impact of that foam might have. So if that foam has the property, I kind of think maybe it does. In between here and here, maybe you have an insulator. Okay. Some way that the charge inside here can't get out and neutralize the charge in the capacitor. We have a bunch of positive charges here. A bunch of negative charges here. And the field between these two plates pulls negative charges within the dielectric to this side. Not as many of them as we have positive charges here, but maybe half as many, and positive charges to this side. And what's that do to the electric field? Well, that neutralizes some of this positive charge, because if you draw the Gaussian surface, here, there's less net charge inside that surface. There's going to be less field. And well, this thing's called the dielectric. Okay. If you had a water filled container in here with insulators around it, and that's not really practical because water is going to find a way to decompress everything up. But if we did, it would actually pull, well, it would turn the polar molecules of the water so that the negative side would be facing here and the positive sides would be facing here. So the water molecules would tend to line up a little bit that way. That's so effective that you shield almost 99% of the charge. Okay. So good dielectric can approach reducing the electric field by 99%. What you get? Field's reduced. For some factor. We symbolize that factor by positive K, or by capital K. Field reduced by factor K. So the voltage of the capacitor is reduced by factor K. Which means that if we have this thing hooked up to source, we can get K times as much voltage for the same potential difference. Okay. Now I say we get K times the charge. we're gonna need K times the charge in order to get up to the voltage of the source. Okay. Which means that the capacitance becomes K times as great. Because we're gonna be able to put K times as much charge on there. Whatever the voltage of the source is. It's a capacitance is charge per unit of voltage. Going to get K times the capacitance. There's the bottom line. And that's an explanation. That's pretty much what the explanation is. You don't have to go to quantum mechanics. You don't have to go a whole lot deeper than just rotation of polar molecules or migration of charge within the dielectric. Okay. Usually isn't migration, it's usually some kind of realignment, I think. And I'm not a material scientist, don't know that much. Okay, well, that's, I think. I mean, I've just introduced everything in the chapter review. Okay, talked about it. And unfortunately, we don't have another class this week because these in service days. Combine that with the class that we missed due to snow in some parts of the country. And we're a little short on time. And I'm not sure how I can adjust schedule, of course, to accommodate that. But in any case, get into this stuff. There's some pretty tricky questions about capacitance and stuff. Use these principles or combine it with formulas. Think it through. You'll be able to answer a lot of them. Some are pretty darn confusing. Okay. So do your best with it. And kind of go from there. Now, one more thing.